I'm not involved. What's the picture of?
Oh, it's standing on El Capitan, about 2/3 of the way up, looking down into the forest below.
Excellent.
And of course, the picture is not claiming that those feet are Scott's feet.
Yeah. It's the spot is actually called the glowering spot. You're meant to stand there and glower at everyone below you.
Okay, so I think it's time for our next session. I guess everybody is back from the breakout rooms. And now is finally the time, after all this algebra, to start doing some interesting mathematics. And so we have...
Hey, go to hell.
So now we have Alex Best, who is actually a number theorist in Boston, preparing a PhD in number theory. And he has been playing with Lean for, I think, since fall 2018, I guess.
About 2 years.
About 2 years, and he will explain how you would build topological spaces in Lean if you don't want to use what's already there in Mathlib.
Yeah, okay, thank you, Patrick. So can everyone see this? Fine. So,
yep.
So yeah, we're going to talk about building topological spaces from scratch. So Lean does have a large library, or Mathlib rather, has a large library of results. So Tikhonov's theorem, stone check compactification. And maybe Patrick will tell you more about those, or there's a link here. But today we're going to ignore all that, and we're just going to work from the beginning and define a topological space and a metric space, just to kind of see some of the issues that come up with these definitions in a kind of simplified version. The one in Mathlib you'll see is a lot more involved. There's a uniform space, there's a topological space, there's a metric space on top of that. So this is a kind of a cartoon view maybe that will teach us the important lessons that have been learned by the Mathlib maintainers while implementing topological spaces. So as before, if you haven't run Lean Project Get Lean for the Curious Mathematician 2020, you should to get this file. It's in Wednesday afternoon. And if you haven't recently, you could run git pull to get the current version. I've updated this a little bit today. Maybe you have one from earlier, it's not going to be too different, but if you can, try and run git pull. So I'm just going to talk over this file for maybe 20 minutes and just kind of highlight the exercises and the key lessons that we can learn. And then it's over to you to fill in some of the exercises and to ask questions and to read through some of these sections maybe again, because some of them I'm going to go over a little quickly, just so that I'm not talking for a long time, and the explanation is there in the text. So yeah, setup. We can't compute with real numbers. We're going to define metrics, so we're going to add this at the start, just so that we don't get annoyed by Lean telling us everything is non-computable. And we're also going to use sets. So yesterday, Jeremy told us a lot about how to use sets in Lean, and that's all going to be applied here, right? Topological spaces are sets, sets of sets. So we're going to be using some of those lemmas. So if we went to Wikipedia, we would see a definition of topological space like the following. It's a pair satisfying some axioms. And if we just translated that directly into Lean, we would end up with something like this. I'm not going to explain all the axioms, but I will note a couple of things. The first of all is that sort of by the Wikipedia definition, you include the X, the underlying space that you have a topology on, as part of the type, right? It's part of the class here, and it's kind of bundled in. And actually, we don't really want to do that. If we do that, it's kind of harder to make other assumptions about this type in addition. So we might want to say we have a finite topological space, and that might be a little bit harder to do if it's kind of baked in. So instead of considering topological spaces as pairs, we're going to consider topologies on a given set X instead. So I'll show you that in a second. And the other thing is that some of the axioms are a little bit unwieldy, right? Finite intersections is a little bit harder to deal with, and it's equivalent to just having pairwise intersections. So a kind of a cleaned up definition of a topological space. It's very similar, but we only assume pairwise intersections because it's easier to prove that things have pairwise intersections. And so it's easier for us to show something as a topological space in this way. And the other difference is that it's a topological space which takes a type here as a parameter, rather than as being bundled as one of the fields of the structure. The other minor difference is that here we're defining is_open as a proposition, right? A predicate on sets. So sets can be open or closed by this predicate, instead of giving a subset of subsets of X. So these are equivalent, right? Like we talked about yesterday, But this way works a little bit better, we found, with some type classes, and also notationally, it's maybe a little bit easier to say this set is open than to say this set is in this weird thing tau. So that's the topological space. And once we've set it up like this, we can use these axioms to prove basic results. So I won't talk about this in too much detail, but here I'm proving that the triple intersection of 3 open sets is open just by applying the axiom intersection a couple of times, as you would. And now we come to the first exercise, which is, it's kind of silly, but it's an important point in general, that one of these axioms is kind of unnecessary. So the exercise is to identify the unnecessary one, the one that follows from the others, that is, and just delete it and reprove it as a lemma based on the others. And this might sound kind of silly, but it is useful to make your structure as simple as possible, so that you don't have to later on keep on reproving things every time you want to make a new topological space that are actually following from the other axioms. So here's the most basic topological space that you could ever come up with. It's the discrete topology. So here, every set is open. So if I take a set, whether it's open or not, it's always true. And then all the proofs are trivial. I can just write trivial, which is this tactic that deals with, well, trivialities. And obviously, because this is always going to output true, everything is just true all the time. Every set is open. So every union is open. Every intersection is open. There's nothing to prove. So this is the easiest one. So this is the one that I've done, and I've given you harder ones to prove yourself. So defining topological spaces by giving a set of open sets is fine, but it's probably not the way you actually are going to go about doing it in practice. What you want to do rather is to define the topology generated by a given set of opens. Right? So you take the course's topology that contains a given set as open sets. So you might define the topology on the reals by taking the topology generated by open intervals. And so this exercise is going to lead you through doing that. And that's a little bit tricky. So I've given you an example of something very similar here, which is how to define whether a set is constructible in the topological space. So this is a concept that comes up in algebraic geometry, at least. But a constructible set is a finite union of locally closed sets. So this is an example of how you define the predicate like that inductively, right? A finite union of locally closed sets. You can define that by saying what a locally closed set is, and saying that that must be constructible, and by saying that any union of constructible sets is then constructible again. So this is quite a clean and natural way of giving a predicate like that. And the exercise for you is just to read this and understand it, and then to give this definition here, the definition of the set of open sets in the topology generated by some given set G. Okay? And obviously that's a really important way of constructing a topological space. And once you've done that, you should be able to fill in all the other axioms of the topological space using your definition, right? So if you've done something wrong up here, you won't be able to fill in one of these sorries down here. Oh, and I should have said, I've marked all the exercises as short, medium, and long, just to give you some idea. Obviously, these are guidelines, and you shouldn't feel obliged to do the exercises in any order. You might want to skip the first one or skip this one to focus more on some of the stuff on metric spaces, because I think it might be hard to cover all of them. In fact, I really do think it would be very difficult to cover all of them. There are maybe 7 or 8, and none of them are too trivial, I don't think. So this exercise, you could also skip for sure, is to give the indiscrete topology using this definition. And it's quite hard to do without this definition, but it's straightforward with this definition. Okay, so now we've done the kind of the setup, we're going to come to the main issue of the talk, which relates to products, for an example, and metric spaces. So if we want to define a topological space on a product, right? So if I've got X and Y, the topological spaces, I can make a topological space structure on the product X times Y, right? The type containing pairs. And I can do that by just using this generate from thing that you've just defined, or will have done. So it's generated by the boxes, right? If I take an open set in, say, the x-axis and the y-axis, and I take the product of those things should be open. And so I take the courses topology containing those things. So that is there for you. And this is a lemma that I didn't want to prove because it's long. So we're just going to take this as a fact. So now metric spaces, which is the kind of the second step in this two-step topological hierarchy. Here's the definition I've given. The only thing that's maybe unusual about this is that the metric here is a distance function from x cross x into the real numbers. And it's symmetric and it's 0 if and only if the 2 points are equal, and it satisfies a triangle inequality. So the unusual thing is that we don't assume that this has non-negative values. And that's because, once again, this follows from the other axioms. So here is an exercise, which is to prove that. Right? And once again, this is this philosophy of like, make your axioms as simple as possible. It's easy to make it as easy for yourself later to write down such a distance function by not having to prove that it lands in non-negative numbers, because that follows from the triangle inequality and these other axioms. So this is a fun little calc style proof.
Alex, do you mind if I interrupt you because
Not at all, please go ahead.
We should say that we are not completely consistent in not putting redundant axioms in our definitions. So maybe if you are really into minimal definition, you were shocked by Kevin's talk defining rings, because in the definition of a ring, you don't need to assume that addition is commutative. Commutativity of addition follows from distributivity of multiplication of addition. Yeah. So somehow we are not consistent in really getting rid of all those redundant axioms.
Yeah, that is true. You don't have to do it, but yeah, sometimes you should see, am I getting annoyed every time I define a blah, blah, blah? I have to prove this thing, and I know it follows from the others, and then maybe I remove it from the axioms. But you don't have to. It's not a rule. Thank you, Patrick. Okay, so now we come to the important point, which is a metric space, right? This metric space basic I've defined is automatically a topological space, right? By this construction, we've hopefully all seen, where you just say the open balls are open sets, right? Balls around a given point x of a certain radius are all open. And that's like a forgetful functor. You could think of it as metric spaces going to a simpler category of topological spaces, right? Or, you know, a less restrictive category. And this is where some of the issues might come from, because this looks very reasonable, right? I define metric spaces, and I observe that each metric space gives me a topology, right? I haven't done anything unusual, right? But we'll see that this does actually cause some problems, and we'll try and rewrite things to avoid these problems. And the problems come when you involve products again. Remember, we defined the product of two topological spaces. And so now we can define the product of two metric spaces by taking the metric to be the maximum of the metrics in each component, right? So yeah, this is the metric where the distance between 2 points is the largest distance when you project down to each of the two axes. And this is reasonable, once again, nothing strange going on here. And now we come to try and prove a quite simple lemma. I take the self product of a metric space with itself, and I'm taking this sort of fattened diagonal, right? I'm taking this sort of open tube around the diagonal of distance 100 here. And I want to prove that this open tube around the diagonal, right? So this is the set of pairs where in the original metric space, they're at most 100 away from each other. And I want to prove that this is open. Not a weird thing to do. And I try and use this lemma we had from earlier, that in a product of two topological spaces, characterization of the open sets, right? And it fails. And by now, probably we will see in a kind of an error message like this, rewrite tactic failed, didn't find an instance of the pattern in the target expression, is open blah, and yet the target is exactly is open blah. What's going on here? Lena's saying it can't find this in this, but obviously These look, this is open of something, and that's is open of something. So something strange has happened here. And what's happened is that the type class mechanism, the thing which finds topological space instances for us automatically without us having to say what topology we're talking about all the time, has got a bit confused. So it's confused because we have two topologies now on this product, x cross x. How come? Well, we have x as a metric space, so it's a topological space. And so it has the product topology with itself, just from the two topologies. But we also have x, it's a metric space, so its product with itself is a metric space. And so that thing has a topology induced by this forgetful functor again. So that you can see there are kind of two different ways of getting topology on this product space, right? One coming from each topology on its own, and one coming from the metric on this product space, and then topology. So this is called a diamond, because you can think this kind of diagram of functors, you go around two ways. And of course, mathematically, you get the same thing, right? There's no mathematical difference between those two topologies. But the type class mechanism, it's a non-trivial proof, right? That you're taking something generated by open balls with this metric, and the topology induced by all those open balls is the same as taking the open balls in each individual component and producting those together. It requires a little proof. And the type class mechanism cannot fill in that little proof. So here, we'll see, this type context is definitionally equal. And we see it's doing some stuff here, and it's saying it's failed to show that this notion of is open is equal to this notion of is open. And this only happens for the metric spaces. If I just prove something just about a topological space, this lemma succeeds. So there's nothing wrong with this lemma per se. Here, success, and it goes and does a bunch of other stuff. But it's just because we have two different ways of getting a topology, and even though they're mathematically equal, the type class mechanism can't automatically check this sort of thing all the time, because it would be too slow. Also, I think you wouldn't want it to be trying to make non-trivial proofs as it goes and tries and finds topological spaces for you. That would make it unbearably slow, I believe. Another lemma is that this example, sorry, another exercise is that this example lemma is false. You can go and fix it if you like. And now let's talk about how to actually fix our definition of metric and topological spaces to avoid this sort of problem here. And the fix is something that's also quite reasonable, is you just bundle the topology in with a metric space. So instead of saying a metric space induces a topology, you define a metric space as a metric space is a topological space, which in addition has a metric in such a way that the metric induces the topological space you started with. So you're just saying a metric space, instead of having a forgetful functor, is just an extension on top of a topological space. And mathematically, these are completely equivalent, but it means that this forgetful functor now isn't something constructed from the metric. It's kind of, you're stacking one thing on top of each other, and then your forgetful functor is just look at the bottom thing you started with. Does that make sense? And this avoids all the problems. So with this definition of metric space, which is a topological space with a metric structure on top of it, this is the definition we made before, in such a way that they're compatible, we do not see the same issues. Okay, so just as an observation, we don't want to have to give a topological space every time we construct a metric space. We can just use one of these, take the induced topology, and we don't need to worry. And finally, we can define this product space properly. And so how is it defined? You take the product of the metric spaces, and then the topology is defined to be the product of the topological spaces. So now the topology isn't coming from the product metric. The topology is the same one we started with on the product of topological spaces. And then you'd have to prove that they're compatible, which I didn't do. But hopefully you believe me that this is provable. And if you'd like to prove it and show me how to do it, I didn't try too hard, but yeah, feel free. That's not an exercise. That's just, yeah, something for fun. Okay, I'm almost done kind of going over the file. Hopefully it wasn't too quick, but if it was, feel free to ask me or the tutor for more explanations during the session. There's a couple more exercises. Here we prove the lemma that we tried to rewrite earlier and failed. And so here we see that it works this time. With this new definition of metric space, not metric space basic, we can rewrite this thing the type classes don't get confused. We don't get a weird red underline and some confusing error message. And then there's a couple more exercises down here at the bottom, proving proving that you can construct a metric space, a topological space, starting with a set of closed sets rather than a set of opens. Some fun exercises in manipulating sets. Probably a little similar to yesterday, except we're going to be taking the complements of sets and intersections of the complements and lots of things like that. So this might be a little long, but I think you can all do it with the tools you learned yesterday. And then there are some joke exercises at the bottom that you can read if you're a more intermediate or advanced user and have seen all this before. So that's all I have to say. I think. Are there any questions?
Yes, Alex, one question. So I've seen that all over the file you define topological and metric spaces as classes. And what's the advantage of not having structures but classes while defining them?
So yeah, a class is a structure, but it's a structure that's registered with a type class mechanism. So that means, so for example, down here, this is, I take x cross x here. I didn't assume that x cross x had a metric. I just assumed that x had a metric. And Lean went away and automatically found that I'd already defined as a class how to define the metric on a product.
You already defined as an instance, you said.
Yeah, sorry, as an instance, this one right here. So as an instance of the class metric space. And so Lean found this automatically because it was a class and not just a structure. If I made it a structure, I just assume a metric space here, and then when I wanted to do this, I would have to say x cross x and then somehow specify with the product metric. In addition, and it would be a lot more verbose, basically.
I see, okay.
I have a question. Is it true that whenever we have two instances, then Lean just complains, like in this case here?
No, it won't complain in general, especially if they are definitionally equal. But otherwise, it will pick the first instance that it finds. But if you really have two different instances of the same class on the same type, this is probably not what you're wanting to do. I mean,
but
you
probably
have confusing stuff happening.
Yeah. But in Alex's example, the Lean complained about how to
yes,
find
because the two instances were not definitionally equal, and he picked Lean picked the wrong one, and then nothing made sense. Really, this is completely unnatural from a mathematical point of view. This trick of saying that a metric space is a metric and a topology together with a compatibility axiom. But really, it's only shifting around this lemma, saying that the product metric is compatible with the product topology. You need to prove it at some point. So the only difference between the real world and what we are doing here is the place where this proof happens.
Yeah.
And how. So you need this fact, which is not completely trivial. You need to write a proof even in the real world.
I see.
And so what Alex explained, but it's normal that it takes time to sink in. I mean, it is you need to get used to this and have more time and to think about this. Is the kind of technological trick that tells you how you should set up things and where this proof should go, so that then you can use it without being conscious that you use it.
I see. Thank you.
Thanks.
Okay. If there are no more questions, Patrick, shall we start breakout rooms?
Yes, I think so.
Okay. And then maybe, Scott, can you stop the recording?